Hey, 12th graders. So we're back. We're talking about more different kinds of exponential models, but I know that this is starting to feel like maybe we've got a lot going on in this unit, but I hope that you're starting to see that it's really just the same idea showing up in a bunch of different ways. So we're going to talk again about exponential models. We are going to quickly sketch out what each of these graphs look like, and I'll show you, we could put them into our graphing calculator and quickly sketch them. So if that's something that you want to practice and join along in doing, I encourage you to go ahead and just do it while I'm talking. But I'm going to also show you how I know how to do this, at least quickly, to quickly sketch out ideas of graphs, exponential graphs. So an exponential graph that has a base of 2 and it's raised to an x power, how we know that something is an exponential function is when your variable is in the exponent, by the way. So that's what the defining factor is about all of these formulas that we've been doing, is that your variable is in the exponent. So 2 to the x power. At 0, when it doesn't have like plus or minus anything or multiplied outside of this exponent piece, at 0, we raise 2 to the 0 power, it's 1. That's going to be the same for all of these guys. It's all going to intersect at 1. When we do 2 to the first power, it then becomes 2. 2 to the second power, it becomes 4. If I did 2 to the negative 1 power, 2 to the negative 1 is 1 over 2 to the first power, so it turns into a fraction. I like to think of it that it goes up by double on this side, but here it goes down by half on this side once I cross to the negatives. If it's a 2 as my base, it goes up by double on the right side, goes down by a half on the left side. So this is what that graph would look like quickly sketched. The next one would be 1.5 as my base. So looking at what's the same and what's different between these functions, 2 to 1.5, it's just slightly less than 2. If I raise this to the 0 power, it's still going to cross at 1, so that's the same. But if I raise it to the first power, now it goes up to 1.5. If I raise it to the second power, it goes up to 2.25. How do I know that so quickly? It's like 15 squared. 2.25, 225 is 15 squared. So that's the kind of cool thing about our Hindu-Arabic numeral system, is that we can just kind of move decimals around and think about them in that way before we reapply where the decimal goes. And you can kind of see that what's going on is that this graph still increases, but it's not increasing as steeply as this guy was. It's just a little bit squished down. Interesting. Okay, 0.5, thinking about it formulaically, maybe coming up with a hypothesis about how this graph is going to look slightly different. I'm going to go ahead and start drawing out a few things. At 0, it still crosses at 1. At 1, it is 0.5. At negative 1, it's 2. It's like 1/2 raised to the negative 1, just like this guy flipped over here. Now it'll flip this way. Raised to the negative 2 power would be positive 4. And so then this graph looks something like this. Interesting. Was your hypothesis, your guess that you had made in your head, the same as what it came out to here? Maybe, maybe not. So the difference in the formula, right? 2 to 1.5 to 0.5 versus the difference in the graph. Pause and take a notice. What are you seeing? What's the same? What's different? Why has it changed? Okay, 0.3 to the x power, if I was to graph it quickly. Raising it to the 0 power, still 1. 0.3 raised to the first power is 0.3, and then I would do another third of that. Raising it to the negative 1 power, it becomes, if that's 3 over 10 raised to the negative 1 power, that's 10 over 3, so that's like 3.3 repeating. So it kind of goes up here. So it looks something like this, a little bit steeper than this guy up here, but still going down, still decreasing, right? E to the x. E is just a number. It's like 2.71 something, something, something to the x power. So E, just like pi, is just a number. E is a very common, what we call base. All these numbers here are bases. It's a very common base for an exponential growth. It's called Euler's number. And it's pretty freaking cool. Euler, but spelled like that. So raising it to the 0 power, still 1, as I said. Raising it to the first power, it's 2.71. We're going to notice, okay, it's increasing, but slightly more than our 2 to the x power. So if I were to go down here, how can we tell if an equation is increasing or decreasing exponentially? Go ahead and take a guess. Write out your guess to this right now. Okay, so hopefully you noticed that there was some difference in the formulas, difference in the bases. Now, this is just one way that might determine how an exponential model shifts. Sorry. So exponential models can shift around. There's a lot of other variables going on here. As we'll see, I can even tell you one of the general forms is y equals ka to the rx plus c. So I'll talk about what all these pieces mean, but you can see that this function is more simplified down than this function. So all of this to say is that one way that we can determine whether something is increasing or decreasing and how much it's increasing and how much it's decreasing is the base, which is this a right here. A is the base. And you can see that if the base is bigger than 1, it will be increasing. So increasing if the base is greater than 1, excuse my shorthand, decreasing if it's less than 1, but very specifically if it's between 0 and 1, if it's a decimal, right? So if it's 0.5, 0.3, if it's a decimal or a fraction that is less than 1, but above 0, then it would be decreasing. Less than 1. Okay. So we're going to label the graphs that might represent a cooling temperature. Let's just do it this way. This is representing a growth, right? Anytime we have like a bacteria growth or population growth, anytime we're thinking about growth, this is what an exponential growth will look like. This is helpful for when you get to a problem and you see that as an exponential model and you're going to think, okay, I want to have a visual representation of this relationship as well as a formulaic representation. This will be your visual representation. Draw this out real quickly to be like, okay, this is what a growth looks like in an exponential model. Versus a decay, it would be helpful to just draw out just a quick sketch of like, okay, this is what a decay would look like to kind of help you figure out what's going on there. All right. A few of the basic things to look out for, things that have exponential modeling. Population models are typically exponential models. Compound interest, which we've already seen, is an exponential model. Of course, geometric sequences in series, which is a percent change, right? So we've put all of these into our exponential modeling unit, and these are the main ways that you'll see models that are exponential. Okay, we've talked about A being the base. Another way that determines whether we will have a growth or a decay is not just A, but also R. Sometimes we have an R value. When you have an R value and R is greater than 0, this will indicate a growth. In other words, when it's positive, right? If R is greater than 0, so if this exponent up here is positive, there's no negative sign, then it's going to grow. Versus when R is less than 0, then it's going to decay. So if it's a negative exponent up there, then it'll decay. Of course, if you have a decimal with a negative exponent, then those two negatives will undo each other and it'll become a growth, right? If you have a positive exponent and a negative or a decimal base, right? This is a positive exponent, but a decimal base, it's a decay. So these relationships kind of play off of each other and can kind of flip things around. Kind of think about like a positive multiplied by a negative is a negative, but a negative times a negative is a positive. It's kind of like that relationship. So I know that this might be confusing because there's not one set rule, but it's just because mathematics is all about a relationship of pieces going together and what it means with all of these pieces coming together. And so just realize it's a relationship of multiple things. So A determines growth and decay, R determines growth and decay. They can also flip each other around sometimes in an equation. A couple other things that I want you to keep in mind. The cool thing about exponential models and why exponential models are important is that we have this idea of a horizontal asymptote. And that asymptote can be easily spotted in your equation. Your horizontal asymptote for all of these guys has been 0. And it's because all of them did not have a C value, or rather, it was adding 0 at the end. So your horizontal asymptote is the equation y equals, and then whatever that value is for C. So why does population growth become an exponential model? It's because at some point your population tapers off, whether that's the resources available, whether that's a predator versus prey relationship that balances out or tapers off a population, that it'll eventually stop growing and it'll taper off like that. That's a horizontal asymptote for population growth. When we have a cooling temperature, right, it'll eventually taper off. It won't go down to ice cold if it's sitting at room temperature, right? At some point, it's going to just kind of level off. So horizontal asymptotes are what make exponential models pretty cool and why we use them. Our initial amount we've talked a lot about in all of our other models, right? Our present value or the first term, right? And it is almost very similar to what we've done in the past. Typically what we've done is we've taken K and said, hey, that's our initial value, but it's also because we haven't had any pluses or minuses outside of that. And so that actually messes things up. So K plus C is going to be your initial value. And we'll see how that kind of plays out in our next examples. So if that doesn't make sense yet, if any of this doesn't make sense yet, we're going to continue to talk about it throughout these examples. Something else to keep in mind, A equals 1 plus P. A is this base right here. And if we're talking about percentage growth or percentage change, P is the percentage change. And this is something we've talked about with our geometric sequences in series, where we said, like, okay, if we're increasing by 1%, then you add that decimal to 1. If you're decreasing by 1%, then you subtract that decimal from 1. And this is just kind of iterating that with this exponential model that, hey, your base is the rate of change, but it's the rate of change plus or minus from 1. All right. Let's go ahead and start diving into examples, because sometimes I don't understand what's going on until I get a few examples under my belt.